So first of all, what is a solution? What do I mean by that? Well, we already learned about mixtures. We learned that on during week one of the first couple days of class. And a solution is just a homogeneous mixture. Okay, it's where a mixture where you have uniformity throughout the mixture. Okay, homogeneous. Two or more substances. It doesn't have to be only two substances. And some of the terminology that goes along with solutions is you always will have a solvent. Okay, so that's the component of the solution that's present in the greatest amount. And then we would say that the solute is just anything else that's in the solution that's not the solvent. Okay, so for example, think about air, the air that you're breathing. It's not just oxygen. I mean, you think about, when we breathe, we need the oxygen. But that's not all that we are breathing. Air really is a solution. It is a mixture it's a uniform mixture of several gases, mostly nitrogen and oxygen. And the air that we're breathing is mostly nitrogen. So you could think of the solvent part of air as being the nitrogen, and the oxygen part, the part that we actually use for life, is oxygen would be considered a solute. And then there's of course some other trace gases in the atmosphere, like carbon dioxide and argon and other gases like that. Okay, so some of the terminology associated with solutions: the solvent and the solute, and the solution is a homogeneous mixture. Okay, so there's nothing saying that a solution can't have more than one solute. So think about salt water, like from the ocean. Okay, it has a lot of different solutes dissolved in it. Or think about any sort of like a beverage. Okay, Coke, right? Coca-Cola. It's got lots of different solutes in it. Some of the solutes provide the flavor. Some of the solutes provide the color. Some of the solutes provide the fizziness. So you can have lots of different solutes dissolved in your solvent. And as I already alluded to, a solution doesn't have to be something that's liquid-based. That's typically what we think of, like you dissolve something in water. And that's mostly what we're going to focus on in this course. But like I already said, a solution can be with gases, like the air that we're breathing, or you can even have a solid solution. And a good example of that is like a metal alloy. A metal alloy has a solvent, and that would be the metal that's present in the largest amount. And so the one that's common is steel. You've heard of steel, like steel cans or steel beams or something like that. The base metal, the solvent in steel, is iron, but uniformly distributed throughout that iron is carbon. And so carbon would be the solute in that alloy we know to be, or we call, steel. Okay? All right, so but in this course and in chemistry, we typically deal with aqueous solutions, and that's where water is the solvent. And the way we designate that when we write things out is with AQ in parentheses, and the AQ stands for aqueous. Okay, it's an abbreviation for aqueous. So one way to designate the fact that we're going to put something in water in chemical reactions is like we show right here. We draw the reaction arrow, but then we put H2O above it. And that's just to represent that I have some product, or pardon me, I have some substance that I'm going to put into water. And then what's on the other side of the arrow, of course, would be what that substance forms when it does dissolve in the water. Okay, so for example, let's say that I put sodium chloride, table salt, into water. Well, what happens to it? Well, we know that this is an ionic compound, and it's soluble, so it breaks apart into its component ions. It breaks apart into sodium ions, aqueous, and that means that these ions are dissolved in the water, plus the chloride ion, aqueous. So again, this solid substance breaks apart into these component dissolved ions when you put it in water. So when it comes to solutions, one of the things that's important to know about the solution is the concentration of the solute. Okay, so the concentration, this cat has really good concentration, but that's not the kind of concentration we're talking about here. We're talking about the amount of solute in a particular solvent or solution. All right, that's what we mean by concentration in chemistry. Okay, and one of the units of concentration that we really focus on is this thing called molarity. Okay, it's a common unit of concentration in chemistry. So what is molarity? Well, molarity is defined as moles of solute per volume of solution, and usually that's in, well, for molarity, it must be in units of liters. So it's moles per liter. Moles of solute per liter of solution. That's the definition of molarity.
Mole, 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 mole.
All right, so it's relating the moles to the amount of a solution. All right, so just like we learned yesterday with stoichiometry or 2 days ago when we learned about the concept of moles, it was like, you know, something had a certain molar mass, which is a certain number of grams per mole. Well, with molarity, it's like a certain volume per mole or a certain number of moles per unit volume. So they're similar and they're used similarly. So if we just rearrange this equation, if the molarity equals moles per liter, then I can just multiply both sides by the number of liters, right? The volume. So multiply times volume, multiply times volume, and I isolate the number of moles. And so, which we're going to represent with a lowercase n, okay? So that number of moles we can say is equal to the volume in liters times the molarity. Because that's just, this equation right here is just rearranging this definition of molarity that we have up here. Okay, if we know the volume and we know the molarity, we can calculate the number of moles. All right, and the reason why molarity is so important is because we are going to use it most often as a conversion factor. It is a way to convert between the number of moles and the volume of a solution. Just like we use the molar mass as a way to convert between the grams of a substance and the moles of a substance, we're going to use molarity to convert between the moles of a substance and the volume of that solution, okay? So we're going to use molarity most often as a conversion factor. All right, so for example, what is the molarity of an aqueous solution prepared by adding 36.5 grams of barium chloride to enough water to make 750 milliliters of solution? Okay, so there's several things that we have to do in this particular problem. So first of all, one thing I need to know is I need to know what barium chloride is, right? I just given the name, but I need the formula for that. So barium chloride, remember barium is in group 2, so it likes to form +2 ions. So the correct formula for barium chloride is BaCl2. Okay, so if I need to calculate something, then I also need to know the molar mass of barium chloride. And so barium has an average atomic mass of 137.328, so it's 137.328. And then we're going to add that to 2 times the average atomic mass of chlorine, which is 35.453. Okay, so you do all that math, and I'll do that real quick. You can do it along with me if you want. So 137.328 plus 2 times 35.453, I get 208.234. So 208.234, and that's units of grams per mole. Okay. Okay, so now it says we're asked for what is the molarity. Well, remember that molarity, symbolized with a capital M, is moles, which we'll represent as a lowercase n divided by the volume in liters. So I'll just go ahead and put capital L for liters. So what I have here is a mass. So the first thing I need to do is I need to convert this mass into a number of moles. Okay, that's the first thing I want to do. So I'm going to start with that. So 36.5 grams of barium chloride, BaCl2. And I want to convert that into a number of moles. Well, that's what this is for. That's why I calculated that. So 1 mole of barium chloride, 1 mole of BaCl2 is 208.234 grams of BaCl2. Okay, so grams of barium chloride over grams of barium chloride. So right now I have moles of barium chloride. So then the other thing that I need to do to get the molarity is I need to divide that by the volume, right? It's moles per liter. But what I have here is a volume in milliliters. So if I convert that into liters, right, I just move the decimal place over 3 places, right? So that would be 0.750 liters. And so I can divide that number of moles by 0.750 liters. And this is just a placeholder. That 1 in the numerator is just kind of to, be complete about it. You could do it in 2 different steps if you wanted to. But right now what I have is I have units of moles per liter, which is units of molarity. So I'll get some number and in units of molarity. Okay, so I'm going to let PowerPoint take over from there. And we'll go through it. The molarity is moles per liter. So the mass of barium chloride divided by the volume. 1 mole of barium chloride is 208.2. So if you look at how the units cancel, you get grams over grams, so you got moles per liter, and you get 0.234 molar. That's how you'd say that. You would say this is a 0.234 molar solution of barium chloride. That's the way you say it. Okay, so grams cancel, moles per liter. Molarity of 0.234. Okay, so here's another example, just from a different angle. This asks how many grams of aluminum nitrate are required to make 500 mil of a 0.0525 molar aqueous solution. Okay, so once again, I'm given a name rather than a formula, so that's kind of a pain in the butt, I know, but another important skill to have in chemistry. Okay, so the correct formula would be aluminum, and then nitrate is NO3. Okay, but then it's going to take 3 of those nitrates, because aluminum likes to be a +3 ion. Aluminum is +3. Each one of those nitrates is -1. So I need 3 -1s to cancel out the +3. Okay, and so once again, the molar mass of that is just going to be, round that to 213 grams per mole. Okay, and so how many grams of aluminum nitrate are required to make 500 mils, which that's, move the decimal place over, right? So that is 0.5000 liters. And remember, that's important for the sig fig part of it, right? The reason why I write it out that way is to illustrate that we got the 4 sig figs, okay? And in this one, you got a molarity of 0.0525, okay? So this is a good question to kind of illustrate, what number do you start with, right? Well, remember, my mantra is you always start your calculation with the number that you're given that's not a conversion factor. But earlier I said that we're going to typically use molarity as a conversion factor. So I know I'm not going to start with that number. The only number that I have that's not a conversion factor is this volume. And I've already changed that to liters. So if you don't mind, I'm just going to start with the volume in liters. So 0.5000 liters. Okay. And so now I am going to use this molarity as a conversion factor. Okay, and it says that I have 0.0525, and remember what this means, moles of aluminum nitrate, so moles of aluminum, NO3, 3, for every 1 liter of solution. So that means my units of liters will cancel, and so right now I'm in units of moles of aluminum nitrate. Okay, well the question is, how many grams of aluminum nitrate? So I need to convert that moles of aluminum nitrate into grams of aluminum nitrate. Well, that's what the molar mass is for, all right? That's what it serves, that's how it serves its purpose. So 1 mole on the bottom of aluminum nitrate, pardon my penmanship again, that's truly chicken scratch, sorry about that, is, and again, I am kind of assuming that this is correct, we'll find out soon, grams of aluminum nitrate. Okay. And so then that will give us a certain number of grams of aluminum nitrate. Okay, it's because moles of aluminum nitrate over moles of aluminum nitrate cancel, and so you end up with units of grams of aluminum nitrate. Okay, so now I'll let PowerPoint take over from there. Good. Okay, so you start with the volume because it is the number that you're given that is not a conversion factor. You multiply that times the molarity to get the liters to cancel, to get the moles of the solute. Well, the question asks for how many grams of the solute, so that's where the molar mass comes in. So one mole of aluminum nitrate is 213 grams of aluminum nitrate, and so you get 5.59 grams of aluminum nitrate. So the idea here is if you wanted to make 500 milliliters of a solution at this concentration, then you would go to the shelf and you find the bottle for aluminum nitrate. You would weigh out 5.59 grams of it, and you would dissolve it in water up to 500 milliliters. Okay, so that's kind of the utility of a calculation like this. Okay, so liters cancel, moles cancel, grams. A notation thing. So when it comes to molarities, a lot of times the abbreviation or the symbolism uses brackets, okay? So brackets are often used to indicate the solution of a substance with units of molarity. And so an example of that would be something like this. So, you know, if they put a formula in brackets and then they give you a number, that would typically mean that's, you know, it means that this is a solute in aqueous solution with a concentration of some number with units of molarity. Okay. So if we have an ionic compound, there's a couple ways to represent the actual concentration, because remember that when you dissolve an ionic compound, those ions are independent. They just kind of float around in solution independently. And so you may see that solution represented as a concentration of the solute as a whole, or as a concentration of one of the component ions. So for ionic compounds, the concentration may be expressed for the formula unit as a whole, or for the component ion. So for example, calcium chloride, okay? So you could say that I have a 1 molar solution of calcium chloride, but remember that within calcium chloride, I've got 2 chloride ions, okay? Because when you dissolve calcium chloride in water, you get the calcium plus 2 ion, but then you get 2 chloride ions, okay? So it is simultaneously a 1 molar solution of calcium chloride, but since there's twice as much chloride in the mix, you could also say that it's a 2 molar solution of chloride ions, right? Because 1 mole per liter of calcium chloride, well, if you, according to this balanced chemical reaction equation, there are 2 moles of chloride ion for every 1 mole of calcium chloride that I've dissolved. So that means that you have 2 moles of chloride ion per liter. So you have a 2 molar chloride ion solution.
That's right, he can be taught.
So this is really just for your awareness that sometimes, you know, it depends on what you care about, whether you care about just the chloride ions or whether you care about the compound as a whole. It can be represented either way. Okay, for the purposes of whatever chemistry you're interested in, you know, it could be represented as a 1 molar solution of calcium chloride, or this solution could be called a 2 molar solution of the chloride ion. Both things are true. Okay, so it turns out that, and I know that many of you are taking this class because you're the environmental health major. I know that it is a required class for environmental health major. Other units of concentration are used in that field. So if you're in the environmental or even, you know, some biomedical applications, you're going to see other units of concentration besides molarity. And that's because in those areas, the concentrations you would talk about or concerned about are very, very small. So they're going to use smaller units. So instead of molarity, you might see millimolar, okay, which is just 10 to the minus third molar, or you might even see micromolar, which is 10 to the minus sixth molar, okay? Or sometimes you see them as part per million or part per billion. So ppm or ppb, okay? So part per million just means that it's sort of a mass-based relationship rather than a mole-based relationship. 1 gram of solute per every million grams of the mixture. Part per billion is 1 gram of solute per billion grams of the mixture. Now, in this course, I won't have you doing any calculations with part per million or part per billion. This is just really for your information. But conceivably, you could be asked a question about millimolar or micromolar, but that's just a prefix thing. It's nothing more than that. Okay. All right. So now that we know about units of concentration, molarity, we want to talk about how to calculate and how to do and calculate dilutions. Now, what do I mean by a dilution? So, you know, you're familiar with the word dilute. To dilute something is to make it, you know, weaker, right? So we do that a lot in chemistry, particularly in the laboratory. So when you do that, you usually start with something that we call a stock solution. A stock solution is just a concentrated solution that we use to prepare solutions of lower concentration, okay? That's what we mean by a stock solution. And so, for example, household cleaners, right? A lot of times household cleaners are sold in a more concentrated form, and you're supposed to take like a bottle cap of it and dilute it into a bucket of water or something like that. So it's something that I think most people are familiar with, the idea of diluting a concentrated solution into something weaker. In chemistry, we would just call the starting solution a stock solution because it's more concentrated. Okay? So dilution is just the process of lowering the concentration of a solution. And how do you do that? Well, you add more solvent. So, like the household cleaner example, I take a bottle cap of the household cleaner, and what do I do with it? I add it to a bucket of water. So that's essentially you're adding more solvent to it. All right, now the key here is that when you're diluting a solution, the number of moles in the solution does not change, only the volume. The amount of solvent changes. Okay, so the number of moles stays the same. It's just the volume of solvent that changes.
Mole, 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 mole.
All right, so the way we would represent that with an equation is that, remember, lowercase n we're using to represent number of moles. So the moles of solute initially will be equal to the moles of solute diluted. Okay, so now we're going to expand that out because we've learned earlier in our notes, we wrote an equation for calculating the number of moles. Okay, so but this is just kind of a picture to illustrate what we're talking about here. So down here is my stock solution. So it's a darker blue, and over here is my diluted solution. So on the left here is my concentrated stock solution, and on the right over here is my diluted, less concentrated solution. So a darker blue, lighter blue. Okay, so typically the way this is done in a chemistry laboratory is I would use a pipette. So this instrument right here, this thing with the 25 on it, that's what we would call a pipette. And so the 25 would represent 25 milliliters. And so these are used because they can very accurately measure out 25 milliliters. Or you could have a 10 mil pipette or a 5 mil pipette. It's just, they're standardized to measure a very accurate volume. So I would draw up from the stock solution 25 mils. And then I would put that in another flask. So I pull it out of here and I dump it into this new flask. So then I take that flask and I add distilled water to it. And this is what we call a volumetric flask. And so on this, you can't see it in this picture, but on the neck of this flask, there's an etched line. And so I would add distilled water up to that etched line to get, again, a very accurate volume. And so then I take what was 25 mils and I add solvent up to a certain known volume, usually in this case probably 100 mils, who knows, but it's some known volume. Okay, so all of that is just kind of a background explanation, because what's most important is the moles of solute that I have in this sample is what I put into this flask, and then all I did was I just added more water. So the moles of solute in this flask over here on the right is the same number of moles, okay? Moles initial equals moles diluted, is the same number of moles of the solute that I pulled out of my stock solution. So I start with a certain number of moles from the stock solution, I put it in a new flask, and with that new flask, I added some more water to dilute it to a new, larger volume. So it started with 25 mils with a certain number of moles of solute, but then I just diluted it up to another new, larger volume. So it's the same amount of solute, just a larger amount of solvent. Okay, but this is where I start with this relationship here, that the initial number of moles is equal to the diluted number of moles. And so as I said before, what we're going to do is we're going to replace these with an equation that I learned earlier in the presentation for calculating the moles of a solute.
Okay.
What I showed you was that according to the definition of molarity, if I know the volume and I know the molarity, if I multiply those two together, it gives me number of moles. So the volume initial times the molarity of that initial concentration, stock solution, is equal to the number of moles I have of that solute in the stock solution. Well, the same thing is true over here on the right side. It's just that it has a different volume and so they're in a different concentration, okay? So the volume of the diluted solution times the molarity of the diluted solution equals that number of moles of the diluted solution. Well, since those two are equal to each other, I can take out the middleman here.
How you doing?
Parts together, which leads me to this very important new equation. Okay, so, and this is the way that it's written on your equation sheet. This is the equation that you will always use when you're doing dilution calculations. M1V1 equals M2V2. Or you could think about it this way. The molarity initial times the volume initial equals the molarity diluted times the volume diluted. Or the molarity of the stock solution times the volume of the stock solution equals the molarity of the diluted solution times the volume of the diluted solution. Okay, so all of that work, all that talk is really meant to just show you the derivation of this equation right here, this equation that we're going to use in dilution calculations. Okay? All right, so let me just do an example of one of those. So this problem says the hydrochloric acid is sold as a 12 molar stock solution. What volume of stock solution is required to make 500 mils of a 0.145 molar HCl solution? So you get the idea here is that we're going to take some of this 12 molar stock solution, and we don't know how much. That's the question. How much are we going to take out? And we're going to dilute it up to 500 mils to make a 0.145 molar HCl solution. So it was at 12 molar, but we're going to take some out and we're going to dilute it up to 500 mils so that it results in a 0.145 molar HCl solution. And so the question is, what volume? So we want to figure out the milliliters that we want to pull out. So the equation to start with is always M1 V1 equals M2 V2. And then you just kind of fill in the blanks. You know 3 of these 4 terms. So molarity 1 is 12.0 molar, all right? That's the concentration of the stock solution. And the question is, well, how much of that? So I don't know volume 1. That's what I'm trying to solve for. How much of that stock solution do I need, of that 12 molar stock solution do I need in order to get molarity 2, which is 0.145 molar? And I know the volume that I want of that, it's 500 milliliters. So you can either leave it as milliliters, or you can change it to liters. It doesn't really specify, as long as all your units are the same. Molarity and molarity are the same, volume and volume are the same. Those units just need to be the same. Okay, so now I just rearrange this to solve for this term right there. So the volume 1 would be equal to 0.145 molar times 500 milliliters divided by 12.0 molar. So units of molarity will cancel and we'll end up with units of milliliters. Okay, so it's as simple as that. These are typically pretty simple calculations. It's just I think most students just have a little difficulty determining how to get started. And so the key is recognize in the question when you're doing a dilution. And if you recognize that you're doing a dilution, you always start with this equation. That should be the first thing you write down. Okay. All right, so PowerPoint. So M1 V1 equals M2 V2. This is just a different way of writing it, right? Rearrange, solve for the thing that you're looking for. In this case, I'm looking for the initial volume. Just move the other term over to the other side by dividing both sides by molarity initial. Substitute the numbers that you know, 500 mils times 0.145 divided by the 12 molar to get 6.04 mils. So the idea here is that you're going to take 6.04 mils of this concentrated 12 molar stock solution, and you're going to put it in another flask, and then you're going to dilute it up to 500 milliliters. And so then what you will have is a 0.145 molar HCl solution. Okay, here's another example. So it says 18 mils of 0.25 molar solution of sodium chloride is diluted to 1 liter. And what is the new concentration of sodium chloride? So once again, you can just start with M1 V1 equals M2 V2 and just substitute in the terms that you know. So the initial concentration, the molarity 1 is 0.250. So 0.250 molar is molarity 1. And it says 18 mils of that. So 18.0 mils. Okay. What is the new concentration? So I don't know molarity 2. That's what I'm going to solve for. But what I did was I diluted that up to 1 liter. So I diluted that up to 1 liter, which is, let me just write that in milliliters. So 1,000 milliliters, just to keep the units the same, because I'm going to want them to cancel, right? I need milliliters over milliliters. So that new molarity, molarity 2, is going to be equal to 0.250 molar times 18.0 milliliters divided by 1,000 milliliters. So milliliters over milliliter cancel, and I get my answer in units of molarity. Okay. All right, so M1 V1 equals M2 V2. Substitute in what you know to figure out what you need to find. You need to find that molarity 2. And then if you just do the rearranging and solving, you get 0.0045 molar. So again, if you did this, if you took 0.25 molar solution of sodium chloride and you took 18 mils of it and you diluted that up to 1 liter with just pure water, distilled water, then the resulting solution would have a concentration of 0.0045 molar. So what we need to know is the initial volume of that stock solution. So, we know the molarity of the stock solution. I know what volume of diluted solution that I want, and I know what concentration of diluted solution that I want. So the unknown is that initial solution, that stock solution, the volume of that stock solution that I need to dilute. And so that's what you just rearrange and solve for. And so you plug in the numbers that you know to solve for the volume that you don't know. And in this case, that would be 238 milliliters. So you just dilute 238 milliliters up to 475 mils, and you'll go from 1.3 molar to 0.65 molar. Okay, very good. All right, so now we talked about how to calculate dilution. So last thing to talk about today are these things called electrolytes. So first of all, what are they? Well, the definition is that they are just compounds that form ions in solution. And so from the picture over here, you can kind of get the idea here that, for example, if you dissolve sodium chloride in solution, it breaks apart into ions. You get the sodium ions and you get the chloride ions. And the evidence that you have all these ions in solution is the flow of electricity. And so that's why this light bulb is illuminated, because in the solution, I have these ions which can carry the electrons and therefore complete the circuit and therefore allow the light bulb to illuminate.
All we want to do is pump you up.
You guys are probably way too young to remember Hans and Franz from Saturday Night Live, but so they're very strong guys, right? So you can have strong electrolytes, and so that's when you create a lot of ions. So something like sodium chloride. So when you dissolve sodium chloride, you get a lot of ions, and that's because it, for every mole of sodium chloride that you put into the solution, nearly 100% of it will dissociate into ions. And so we call those things strong electrolytes. So you need to know what type of compounds are strong electrolytes. And they are ionic compounds that dissolve in water, but also strong acids, okay? And we haven't really talked about acids and bases yet. So for now, just kind of, just memorize that fact that strong acids are strong electrolytes. And we'll talk more about acids and bases tomorrow. So something I already showed you, that when sodium chloride is dissolved in water, you get 100% ions. All of these become these. So that's why they're strong electrolytes. Okay, so ionic compounds and strong acids. An example, sodium chloride breaking apart into sodium ions and chloride ions. Okay, and the reason why we consider it a, the reason why we would know that it's a strong electrolyte is that because it conducts electricity efficiently due to the ions. Okay. Well, if you can have strong electrolytes, then, you can have also weak electrolytes. So what are they? Well, they're the compounds that would only partially dissociate into ions. Okay, an example shown over here is acetic acid. Acetic acid is a weak electrolyte. So that is a picture of a acetic acid molecule. And so if you look closely at the particulate, zoom in here, most of the acetic acid is still in the form of a full acetic acid molecule. But a few of them have ionized. Okay, like for example, this one has ionized, and it's donated one of those hydrogen atoms to a water molecule. Okay, so it formed a negative ion, the acetate ion, and H3O+, which is called hydronium. So some of them create ions, but not all of them. They only partially dissociate into ions. Okay, and so it's slightly conductive. And so if you could compare the two pictures here, this light bulb is illuminated, but it's not as bright. Okay, it's not as bright as with the sodium chloride solution. Slightly conductive. Okay, so what type of compounds what type of compounds are weak electrolytes? Well, weak acids and weak bases are weak electrolytes. So again, we'll explain that more tomorrow when we talk a little bit more in depth about acids and bases, but acids and bases can be classified as strong acid or weak acid, strong base, weak base. And so if you have something that classifies as a weak acid, it's also going to be a weak electrolyte. Same thing for a weak base. Okay, so for example, let's say that we have ammonia, NH3. It is a weak base. So the major reaction that occurs, if I put ammonia in water, the major thing that occurs is that it just stays ammonia. It's just that it's dissolved. So let's say that ammonia, naturally, if I had pure ammonia, it's a gas. And so if I were to bubble that gas through a sample of water, It would dissolve in the water, but most of it would just stay in the form of NH3. It wouldn't create any ions. So I would represent that as a reaction like this. So the ammonia gas, when I dissolve it in water, stays as ammonia, but now it's in the aqueous phase. That's the major reaction that occurs. But it does partially dissociate into ions, and so that would be the minor reaction. Less than 1% of it does this. Okay, less than 1% of those ammonia molecules are going to react with a water molecule to give us two ions. It gives us an ammonium ion, and it gives us a hydroxide ion. Each of those dissolved in water. Okay, so that would be the minor reaction that occurs. And the minor reaction does give us some ions, the ammonium ion and the hydroxide ion. So that's why we say it's a weak electrolyte, because most of it does not form ions, but some of the solute molecules react with water to give us ions. So it's a weak electrolyte, partially ionizes. Okay? And that's evident in the fact that this does conduct a little bit of electricity, but it's a dim light bulb, so not much electricity. Okay, so we have strong electrolytes, we have weak electrolytes, but we also have non-electrolytes. So these are things that do dissolve in water, but they don't form any ions. And so, I have a solution. In this case, it's an ethanol solution. So some ethyl alcohol is dissolved in this water, but it doesn't conduct the electrons, doesn't complete the circuit, so I don't get the light bulb to illuminate at all. And so an example of that would be ethanol, the CH3CH2OH. Okay, so these are substances in which no ionization occurs. So there's no conduction of electrical current. And so what you need to know is the type of compounds that are non-electrolytes. And so those are all just molecular compounds. Remember, we learned about that last week. We said that there's such thing as ionic compounds, and there are molecular compounds. So, and remember what molecular compounds are. They are compounds that are composed entirely of nonmetals and or metalloids. Okay, so you can't have any metals in the formula of a molecular compound. Only nonmetals and metalloids, with one exception, or I guess two exceptions. So any molecular compound that's not a weak acid or a weak base. And again, we'll talk about that a little bit more tomorrow. So those are non-electrolytes. Any molecular compound that's not classified as a weak acid or a weak base will be a non-electrolyte. Okay, so examples. So these would be just aqueous solutions of sugar or alcohol. The picture here shows an example of ethanol, alcohol, right? Okay, and here's the reaction that would occur. So this is the formula for glucose, right? C6H12O6, sugar, like the sugar that's in your blood, glucose. So if I put solid glucose into water and dissolve it, it just stays exactly the same. It doesn't create any ions at all. But now it's in the aqueous phase. So it was in the solid phase, I dissolved it in water, now it's in the aqueous phase. But notice there are no ions produced.